Hi, so let's start this season 3 of rank improvement program JEE Advanced 2020, and we are discussing one of the very important assignment, and we have already completed 26 questions, and we are going to start now this question number 27, right? So okay. Here, the question is the reaction that represent correct product. Understand this one that here ozone analysis takes place because of this. There the cleavage takes place, and as a result of this, what happens here? Right, this one is C double bond O and OH. This is C double bond O and CH double bond OCH3. This is the other part, and this side COOH. Let it be like this. Both chlorine atoms will remain unaffected in this process. Okay. Due to this cleavage, what resultant product we have in that one? Here the two CH groups. You'll find that fulfills the condition of beta gamma unsaturation, where the decarboxylation takes very easily. So in this case, decarboxylation takes place, in that you see that this bonded pair of electron will take this hydrogen, and this OH bonded pair of electrons will move towards this one, and this will be moving towards this, and CO2 gets released, right? So what is the result of this? Result of this, now this one is a kind of enol, okay, OH. Let the COH group this time as it is, chlorine here, and this one is out as CO2. I hope it is clear. And this enol is an unstable one. Immediately that undergoes tautomization, and that gives corresponding ketone C double bond O. And now I write this also C double bond O, and there the OH, the region is very clear that it also fulfills the condition of beta gamma unsaturation, and decarboxylation will be taking place here, right? So the remaining chlorine atoms will be as it is. Now, as I explained earlier, this hydrogen is taken, the OH bonded electrons will move towards this one, and this will moving towards this one, and as a result of this, what we are getting now? Again, the similar kind of product here. Now this is the OH double bond, in the CO2 is out, decarboxylation takes place, and here there is Cl, there is Cl. Okay. Now there again tautomization takes place. This is Cl, and this one is not double bond OCl. Honestly speaking, this only is the product with the given reagent, but here the purpose is different, and dehydrohalogenation takes place. With that dehydrohalogenation, right, on both the sides, the Cl, and here the Cl, and this one is C double bond O. When we get this kind of condition, then certainly here you will get like this, because this one is the most stable tautomeric form for this one, and finally this is the product after dehydrohalogenation. Please remember what is missing here. Okay, now move to the option B. One thing here, the Br2 is added, and first bromonium ion forms, and then in general Br minus attacks, and Br2 addition is over with the dibromide formation. But now point is here that as the COH group is present at the suitable place, and that can act as the internal nucleophile, so the Br minus will not be attacking, it's the internal nucleophile preferably attacks. And because of that, here I explain you that initially this will form right there the Br, in there the plus, in here I say this one C double bond O, in there the OH. This is the situation when bromonium forms. And after that, what happens here? This one will be attacking here, and this one is leaving. All that happens with this one, right? So as a result of this, what we are getting? We are getting here the Br on this place, and there is no oxygen. This is the carbon, this one, and there is double bond O. Yes, this is the product, right? In this now move to the next question. Next option C. This is the Diels-Seldar reaction. We say simply Diels-Seldar reaction, and in this case, the product depends on the electronic distribution. This reaction is regioselective. They are the you can say that in the case of two or more possible products, one of the product is the major one. So here also we analyze that which product is the major one and which product will form here the predominantly, or and what is the basis of that one. OCH3 is present in this case. Understand that OCH3 is electron releasing group, so due to that electrons moves, and this is the electronic distribution. Because of that, there is partial negative, there is partial positive. If you analyze this dienophile, this one is the diene. In this dienophile, when we see, we find that COOET is the electron withdrawing group, and so there is partial positive and there will be partial negative. So these two will combine in such a way so that partial positive will interact with the partial negative, and so I write here this one. You take OCH3 double bond, and this one is the partial negative, so it's better to write C double bond O and OET, and this one is the partial positive, right? So now I can indicate that this one is moving here, this will be moving here, that is moving here, and because of this we are getting this kind of product predominantly, right? Double bond is here, this one is OCH3, and this one is C double bond O, and there the OET. Yes, this is the product, right? And we don't have this kind of product. Okay, fine. In the D option, move to the next option D. One thing you remember, that lithium aluminum hydride is having H minus attack, and that reduces, that will give here the alcohol. But when lithium aluminum hydride is present with the AlCl3, that reduces to corresponding alkane. So certainly, if we have to find here the correct option, then relatively we find that A option only with some their conditions. A option is correct because B is certainly wrong. As you know, in C is also wrong, and D is also wrong. Okay, so move now. Next question, question number 28. When optically active secondary butyl alcohol is treated with dilute H2SO4, racemization occurs. You know how racemization takes place. Question number 28 we are discussing how racemization takes place, that you know. A racemic mixture is ideal solution. Ideal solution formation is thermoneutral process. What is this? This one is thermoneutral process. This one you understand, thermoneutral process. It means delta H is equal to there the 0. Delta H is equal to 0. Then next, delta H is equal to 0, then how the process will be spontaneous. If their racemization takes place, this is a spontaneous process. A spontaneous process, and delta H is 0, then only it is entropy what makes this process spontaneous. In delta core, if you consider entropy factor, that should be positive. Delta S must be greater than 0. Also, all ideal process ideal mixture forms due to positive entropic change, right? So delta is greater than 0. Fine. So now let us move here. Next question, question number 29, right? So question number 29 question is there, C5H11Br. What is the question? Question is C5H11Br. When treated with alcoholic QH, treated with alcoholic QH gives alkene B, right? While with aqueous NaOH, two things, just understand here. Let's write here, this is C5H11 and there the Br, which is A, right? And with alcoholic QH, okay, there you take alcoholic QH. For what we use alcoholic QH? Elimination, E2 path, right? Elimination takes place. Elimination takes place there. The sum of the alkene forms alkene B. This alkene is B, right? And that while with aqueous NaOH, if there the aqueous NaOH, that is for substitution, right, gives alcohol C, right? Alcohol C. Here the alcohol forms, right? Alcohol, and that is C, right? Now the point is here. Question is just to see the question. This one is C. When heated with copper gives B. C when heated with copper gives B. One thing be clear, the C is alcohol, and if this is primary alcohol, that on heating gives aldehyde. Secondary alcohols give ketones. Tertiary alcohols, dehydration takes place, right? So when heated with copper gives B, what does it mean? It means not aldehyde, not ketone. What forms? B forms. It means certainly that is tertiary alcohol. It is clear. We have concluded this point that this is tertiary alcohol only, because the tertiary alcohol only on treatment with copper can give alkenes, right? So tertiary alcohol. In that way, if we see some options, then we find that D cannot be, because 1, 2, 3, 4 carbon atoms only. There the C also cannot be 1, 2, 3 carbon atoms. These are outrightly rejected. No need to think here. As C5H11Br, so many options could be there. That's why I just, for the exam purpose, it's good to exclude some examples right now. So we have stricken off two examples, C and D. We have two options, B and A. In this case, one thing you be clear that we are getting B option. Here also A can also be, you understand this one, their alcoholic KH will give double bond, right? If we take here the NaOH, then it can give the secondary alcohol also. Is it correct or not? So there is some suspicion in the case of A, and the B is the best option, because if you take here alcoholic QH, suppose there this one is treated with alcoholic QH, what that will give? That will give CH3 CCH3 and double bond there the CH and there the CH3, right? And if suppose there that if you take here alcoholic QH, I mean to say alcoholic QH gives alkene. If you take aqueous, then what this will give? That only. On this you write here the CH3 CCH3 and there the OH CH2 CH3. Yes, this will, right? So B is the best option. Is it correct? B is the best option for this purpose, right? So now move to the next question. That is question number 30. The compound that will not give iodoform test, right? Question is compound which will not give iodoform test, right? So think here the A option. Let's explore all the options. Learning is important, not finding one solution. That's why I explain each and every option, right? Here I take here the option A. In one thing you see this one HO minus, and there the I2. This one is the condition. So in that case, first hydrolysis takes place, and we are getting here the HC double bond O and O minus, and there the CH3 CH2OH and CH3 CH2OH. This product further on treatment with HO-I2 will be oxidized to CH3CHO, and that CH3CHO further will give CHI3 and HCO minus as it gives. So we can say the A will give the iodoform test. If you take here the option B, that is the secondary one, there the HO minus and there the I2, this gives, because very first this one is hydrolyzed CH3, there the CH, and there the OH, and there the CH3, right? And now you see this one very first alcohol, then HO minus I2 cause its oxidation. Oxidation means this will be giving here the CH3 C double bond O, and there the CH3. And next this already CH3 C double bond O minus, and there the CHI3, right? Okay, now it's clear that even the B gives B. In general, right? C option you take. Now you take here the C option. CH2 double bond CHO. This is also the ester, and so on treatment with HO minus, and there the I2. There the first hydrolysis takes place. You are getting here the CH2 double bond, there the CH, and there the OH, and there the C double bond O CH3 and O minus. Is it correct or not? Yes. Now CH2 double bond CHOH, no doubt CH3CO minus, there is no hope, but CH2 double bond CHOH is basically CH3 CH double bond O, right? CH3 CH double bond O, which gives iodoform test in the same condition. So even I can say the C gives iodoform test, right? Okay, let's take here the D option. D option I take here. This is also the ester. Go for the hydrolysis, and on hydrolysis this will be giving here the CH3 C double bond O and O minus, plus there the CH3 and there the OH, right? And CH3COH won't give, CH3OH won't give. So it's very clear that compound that will not give iodoform test, it is D, right? It's okay. Okay, now move to the next question, right? Here we are moving to question number 31. What is the question? Question, read the question. Which of the following does not occur as represented? Means which one is not feasible. Okay. One thing in the very first itself, it looks very difficult because this is the diazo coupling reaction where N2 plus diazonium is acting as electrophile. And its electrophilicity there depends on there that you can say which group is connected to that benzene ring. If any of the electron releasing group is connected, then certainly that one is releasing electron, and there you can say decreasing its electrophilicity, and that makes it difficult. Here the other side which Gibbs coupling reaction that must be highly activated. That's why this option looks very difficult and very weird. So this one is not happening as represented, I can say, right? There the B option, you know that SCN, SCl, AlCl3, H3O plus and all that. This is the Gatterman cause formylation reaction. There is ortho product as well as the para product. It happens right now. The yield is the different thing. Okay, so fine. There C option if you take here. In this case, let's take here that if you take this option and there is the H plus is given, you will understand that very first here this will be now OH plus, here is OCH3, this one is CH3, but once it happens then there automatically this will be moving towards this one and we'll get here this one is OH, this one is double bond and carbocation forms here, and here is the CH3, right? Let double bond here as it is. This one is the OCH3. You understand this one that if this methyl group shifts from this place to this place, the carbocation will come to this place where it is extraordinarily stable due to plus M effect of the OCH3 that you can understand. So what is the next one? Next one is here. This one is OH double bond and now CH3 group is here. There is OCH3. No doubt the carbocation is more stable one, but aromaticity is lost. So what happens here? There is re-establishment of aromaticity. Re-establishment of aromaticity with the loss of this hydrogen, and finally we are getting here this product, right? Here is the OH double bond and double bond and double bond and OCH3 in there, the CH3, right? Okay, fine, done. This one also you got it. Now just to think of the option D. Option D, ETOH in heat, right? This one is okay. This one is the even process, right? Even process, so you can understand that very first here carbocation forms. So in when we are boiling in this one, then there the carbocation forms. After that, there the 1,2-methyl shift. So you can write here one of the species CH3, CCH3, and there the plus, and there the CH2CH3. This one is the thing, and so after that we are getting this kind of product. So it's very clear, right? So move to the next question. Question number 32, right? So what's the question? Question is, which of the following undergoes nucleophilic substitution first? But the point is, which nucleophilic substitution? Here, all these are the arylic systems. So here the two processes we have. One is, you know that benzene mechanism. Benzene mechanism is elimination, addition, and other one is meson-hemmer complex. Meson-hemmer complex mechanism. This one is addition elimination mechanism. So in this case, as any of the halobenzene is not activated, so certainly it is the right condition for the benzene mechanism, and in the benzene mechanism the first step is the elimination, that depends, that only is RDS, a rate determining step, and So the age of that reaction depends on the acidity of adjacent hydrogen. And which will make that one most acidic? Certainly it is the chlorine, which makes, by virtue of its minus I effect, that makes this hydrogen very much acidic one, and that's why it undergoes substitution fastest. Here leaving tendency is not concerned at all, and here the acidity of this hydrogen is concerned. Fine. So move to the next question, question number 33. Right? What is the question? Question is, which of the following ethers cannot be prepared by Williamson synthesis? First, you have to understand that what is the Williamson synthesis. You recall, Williamson synthesis is the SN2 process. Is it correct or not? This is SN2. And here in general, you know, it is the reaction of there the RO minus Na plus alkoxide over R-X halide, or you can say that RO minus Na plus over dialkyl sulfate, RO S double bond O double bond O and O and R dash. Yes, that is the Williamson synthesis. This one is going to attack here. This is the perfectly SN2 reaction. So in this case, this R dash where the attack will be taking place should not be vinylic, should not be arylic, should not be tertiary also, because their elimination dominates. So in this case, let's take here, if we take two things, I take here this one is alkoxide, then this one is tertiary, this reaction is not possible. Okay, let's take here this one is alkoxide, then this one is vinylic, then also this reaction won't take place. So the reaction is not possible. Okay, now move to the next one, B option. B option, you see this one is, let's take this one is oxide. Then this one is tertiary, then this reaction is not possible. If you will take here, this one is oxide, then this one is arylic system, and so then also this reaction won't take place. Here you take this one, in this case this one is phenoxide, this one is phenoxide. If this one is phenoxide, then this one is the arylic system, and then this reaction is not possible. Okay, now the point is there is one option left, and that option is here, this one. If we take here, this one is oxide, phenoxide, then this part is benzyl, where the SN1, SN2 all are going very well. So this oxide will be attacking over this one, and so this reaction is possible, right? So what is the most appropriate option? Most appropriate option is the D, where this Williamson synthesis is possible, right? Yeah, so we have completed question 33. Move to the next question, that is 34. Okay, and read the question. The compound that will react most readily with NaOH to form methanol. So which reaction is this? This one is substitution reaction, right? And so you have to find here the good leaving group, and that is very apparently here we have the nitrogen, here you can say that oxygen, here the sulfur, here tertiary butyl chloride, CH3 is something, one carbon is missing here, tertiary butyl chloride. So in this case there the Cl is the best, but one thing, the question is, there will react most readily with NaOH. So here you will say that the best leaving group is this dimethyl sulfide, right? And so C is the right answer. Okay, move to the next question, question number 35, right? You see this one, in this case we have the racemic acid, that is optically you can say that a mixture of optically active molecules. There plus and minus means dextro and levo. For the better understanding, I will say that you take even the mixture of R and S, fine, and the other one is alcohol, and that is also optically active, and that is optically pure substance, right? So you know it very well that when this alcohol attacks over this acid, right, so ester forms, and what ester will form, that you see that I write here CH3CH PH C double bond O, and there O CH CH3 and CH2 CH3. This ester forms. In this ester you just check the configuration right now, that how the configuration gets affected. You will find that there is no change in configuration here. This configuration is same. Let's assume that here the configuration is R, so that remains still R. And what about the configuration here on this place? On this place, if this one attacks over this R, means one of the molecule which has R configuration, then there the configuration remains R only. But at the same time, this can attack over the acid which has the configuration S. In that case, you will be getting here the CH3 CH PH C double bond O O CH CH3 and CH2 CH3. This time already clear that here the configuration remains R only, but here you know that if the attack takes place on the acid having S configuration, that will remain S. So here what configuration you are getting? R and R. Here what is the configuration? R and S. So we get the mixture of these two substances where the configuration of the chiral centers are R and R and R and S, and so certainly this is diastereomeric mixture. Diastereomeric mixture. And so one thing you know, that diastereomeric mixtures are optically active, right? Optically active. So let's find here the option. Which of the following statement about the product is correct? You have to find the correct. The mixture, the product is a mixture of two enantiomeric pair, so this one is wrong. The product is a mixture of diastereomers and show no optical activity. It shows optical activity, so this is also wrong. The product is a mixture of diastereomers and show optical activity. Yes, that is correct. The product is a mixture of stereoisomers having same and absolutely identical physical properties. Not at all. Identical physical properties, you know, that is a matter of stereo. They are the enantiomers. Okay, fine. So this one is also done. Move to the next question, right? What is the next question? Question number 36. Okay, what is the question? Which of the following is correct? Which of the following is correct? So let's see here that option A. You see option A. What is this reaction? Here the alcohol reacts with SOCl2. What is this reaction? This reaction is SNI. SNI means a retention of configuration. Is it correct or not? Retention of configuration. So is there any retention of configuration? No. In this case, if you'll see this one, there is inversion of configuration. Okay, but SNI means retention of configuration. Correct. So in this case, what we find there, that there is inversion of configuration. SOCl2 pyridine, when the reaction of SOCl2 takes place in the presence of pyridine, or there the tertiary amine non-nucleophilic base, in that case there the SN2 takes place. So this one is pure SN2. SN2 means what? SN2 means there that inversion of configuration. Inversion of configuration. So is there inversion of configuration? No. In this case, it appears there is a retention of configuration. So this is also not. In this case, HBR options there that see the check there that C there that OH and HBR rates. Then what will happen there? Honestly speaking, in this case, right? In this case, rationalization takes place. Although this is not the correct option because product is entirely different, right? And anyway, there as per the reaction, I can say that there is here the 2-degree alcohol that reacts with HBr. Certainly, reaction proceeds through carbocation intermediate. When the carbocation intermediate forms, then there you will be getting the racemic mixture. Although in this case there is big mistake that you have the pH, that is something wrong, right? So here option D, you see that in this case what happens here, that you will be getting here CH3 in there the H and OS double bond O double bond O and pH benzene sulfonyl chloride. It is just like you can say tosalates, brosalates, nosalates, that kind of better living group. So this is converted to that kind of better living group. There is CH3. Right now KBr is given. KBr, you know this one. Br minus is acting as a good nucleophile now. So there is backside attack. Certainly this one is just like SN2, and you get here the inversion of configuration. Although something is wrong here, also there is some printing mistake, and this one is the pH. Here also I think the mistake is here only. Now I understand. So if the pH, there is the inversion of configuration, we have to adjust with this question as there is some printing mistake. Okay, fine. So this one is, but one thing is very clear, this one is it shows inversion of configuration. Right. So I can say based on all this should be a correct option, but honestly speaking, there is some printing mistake, right? So now, yes. So the next question is 37, right? So which of the reaction is incorrect? You have to find the incorrect option, and let's start with each and every option. Okay. So I think let's take here the A. This is just benzylic acid rearrangement kind of reaction. Here you see I write here the PH C double bond O, C double bond O and D, right? So HO minus attacks, where this will attack on the more electron deficient center, and that is this one. This will go up. So you find here the PH C double bond O, C O minus, and D is here. There is OH now. When this O minus is back, this D shifts from this place to here, right? So as a result of this, what we are getting here PHC, and there the O minus, and this one is not D. So C double bond O, and there the OH, proton transfer takes place, and with that we are getting the PHCD OH in the C double bond O and O minus. What we have, just to see this one OD in there, the CH, all this thing is wrong, right? So fine. What about this option B? We should explore even this one. There, one thing you understand, this question is very beautiful question, right? So OCS3 minus is attacking here on this one, right? This OCH3 minus is attacking here. This will go up, and let me write here. Here, this one is pH. Here, this one is O. There is OCH3, O minus. There is another pH, CH2, CH2Br. Next is this O minus is back, and this one is out. We are getting here this one is now well established O minus. Here we have pH. I just simply change it, please, for the better understanding. I write here the CH2 CH2Br. It's a matter of orientation, right? And this group is basically CH2. I mean to say this is CH2. Understand this one? And there the C double bond O. Okay, this is the C double bond O now, and there the OCH3. Hope you don't have any difficulty to understand this one, right? And now this O minus is attacking on this one and this Br. This is the intermolecular reaction, right? And so with this one you are getting finally this as a final product, right? So this is correct, right? And very interesting also. Now what about this C option? C option, you see that what is there? First intermolecular reaction takes. It's not the HO minus which substitutes. So this NET2 will attack here, and you will get here one of the intermediate of this kind, CH3, CH2, CH, and there is N. ET2 means here ET, there ET. This will have no positive charge. In the CH2, okay, Br minus pushed out, right? So now there the HO minus is attacking. HO minus, where this HO minus will attack? Now there are the two places to attack, this one and this one. Let's say this one is the 1, this one is the 2. Where this will attack? Where the assumed carbocation is more stable, where the deficiency is more, right? As this is the secondary place, so the deficiency is more, and so this HO minus is attacking on this place, and this one is leaving, right? As a result of this, what you are getting? You are getting here now the same product, CH3, CH2, and there is CH, OH, and there the CH2 and NET2. Yes, very interesting. Here all these options are very nice. Okay, fine. Come to the next one. Let's see here the D option. D option, you will find that there is the OH. So certainly you will find that first the protonation takes place. Okay, protonation takes place. Then what we are getting? We are getting here, I can say the PH3C plus. Certainly once the protonation takes place, then as there the carbocation is more stable, so this will be leaving, and this will be HO. H means phenol. Now for the phenol, this one is, phenol is the highly activated one for the electrophilic substitution. This is acting as the electrophile, right? So what happens here? You can say now there will be the electrophilic substitution. For this one the electrophile is available, so this will be attacking here. Done. We are getting this product. So initially, should I explain? Okay, let's explain this also, the mechanism. That here initially you will get here that HO double bond, there the plus double bond, here I indicate H, and there the C, PH3, aromaticity is lost. In order to re-establish the aromaticity, this one is moving here, this will go there, this will be here, and finally what we are getting, we are getting here this as the final product. Okay, thank you. In one sitting you should not discuss more number of questions. I hope you this discussion you'll find it very useful and interesting. Many good questions we got, right? Okay, thank you, thanks a lot.